All right, good morning, everybody at home. Can I get a thumbs up that you hear me and see the board? Okay, so I apologize about today's notes. However, to make things go a little bit quicker, now that I think you kind of have the gist as to how these inverses get created, that we can't use the entire original graph, I tried to save us some time by graphing the inverses for you. Just like I said, we'll be able to get through more problems this way, which is the important part. So I have a picture of what I wrote in for you already. So it is a little bit, of a crummy picture, but hopefully you can have it on your screen at home and you can see it that way, and then you guys have it in front of you. All right, so we are moving into the second section, which is still going to be about inverses. This one's going to teach you about the inverse reciprocal trig functions. So each trig function, sine, cosine, and tangent, had a reciprocal trig function, cosecant, secant, and cotangent. Now you have to see how their inverses work. But in my opinion, it's a little, I hate saying a waste of time because math is never a waste of time. It's a beautiful subject. However, when you are working with a reciprocal trig function like inverse secant or inverse cosecant or inverse cotangent, they have to be converted to an actual original trig function's inverse to use your calculator, because we don't have an inverse cosecant button, we don't have an inverse secant button or whatnot, so they all have to be converted to an original inverse anyway. So to me, we just gotta know who to convert it to, and we can go from there, all right? So I've put up all the important information as to far how the original trig inverses work. So we have inverse sine spits out quadrant 1 and quadrant 4 angles, pi over 2 to negative pi over 2. Inverse cosine, it's kind of like his own little individual animal here. He's the one that spits out quadrant 1 and quadrant 2 angles from 0 to pi. And then we have inverse tangent, who acts just like inverse sine, and he spits out quadrant 1 and quadrant 4 angles from pi over 2 to negative pi over 2. We saw if you take the inverse trig function of any positive ratio, it's going to spit out a quadrant 1 angle, right? But remember, the ratio for sine or inverse cosine or inverse sine had to be between 0 and 1. And then you can take the inverse tangent of any positive ratio and get a quadrant 1 angle. If you take the inverse sine of a negative ratio from 0 to negative 1, it's going to be a quadrant 4 angle. If you take the inverse tangent of a negative ratio, any ratio survived, any negative ratio, it's a quadrant 4 angle. And if you take the inverse cosine of a negative ratio from 0 to negative 1, it's definitely spitting out a quadrant 2 angle. And no quadrant 3 angles survive the cut of any of the trig functions graph. Therefore, the inverses are incapable of spitting out a quadrant 3 angle. Okay. So these are some problems we're going to get into in this section. So let's jump right into an example on how we can use these inverse trig rules to solve them. All right, so guys, anytime they ask you to find an exact value, they expect you to be able to do the problem without a calculator. Could you type this into your calculator right now, literally exactly as it looks, and hit enter and get an answer? Yep. But it's going to be the decimal answer maybe, or a rounded answer. It may not be the exact answer that you can type in. So if they ask you for the exact value, we shouldn't need a calculator. All right, so guys, they asked us, if you can read this, they want the sine of the inverse tangent of 1/2. Okay. Well, guys, let's break it down. If you take the inverse tangent of a ratio, the answer is an angle. If you take the sine of an angle, the answer is a ratio. So the answer to this question is a ratio. The problem is the sine doesn't undo the inverse tangent. So I can't just cross it out and say, oh yeah, the answer is 1/2. We got to think about this. So let's start inside. Guys, first they said the inverse tangent of 1/2. We know the answer to that is an angle, right? What kind of angle? Guys, if you take the inverse tangent of a positive ratio, it's either spitting out a quadrant 1 or a quadrant 4 angle. Which one is it if the ratio is positive? Quadrant 1. So we know this is a quadrant 1 angle. We know the inverse tangent of 1/2 is a quadrant 1 angle. So everybody give yourself an angle that lands in quadrant 1. Okay, nice and easy. Now, draw a right triangle in quadrant 1 based off of that angle. Okay, so basically this got us the quadrant 1 angle that we just drew. Now let's use we know. Guys, if you took the inverse tangent of 1/2, it's because the tangent ratio was 1/2. So the tangent ratio for this angle that we just created is definitely 1/2. Guys, the tangent ratio is O over A, or his new definition was Y over X. So label it O1, A2. y, x. If you're in quadrant 1, would this be a positive value? Yeah, because you're going right and up. Would this be a positive value? Yes. So just make sure you label them correctly. You may have to add a negative sign to something. All right, well, guys, so basically that's done. You've gotten the inverse tangent of this angle. So now what you have to do is take the sine of this angle, and that's the ratio that will be the answer to this question. So what is the sine of this angle that we've just created? Well, guys, if we're going to take the sine of this angle, that's O over H, or Y over R. I am going to have to do some Pythagorean theorem to figure out what this side is, right? So A squared plus B squared equals C squared. 2 squared plus 1 squared is 5. Take the square root of it. The radius must have been the square root of 5. Just a little bit of Pythagorean theorem, and you can find out that missing third side. All right, guys, the answer to this question is the sine of that angle. That's going to be O over H, Y over R. It's 1 over root 5. We don't leave this like our answer. We're going to rationalize our denominator and times top and bottom by root 5. And then you get root 5 over 5. And that's the answer to this question. So you're going to use the inverse to build an angle with the ratio they have given you, and then you're going to take whatever trig function is on the outside of that angle to end up with your ratio as the answer. Okay? So I never even have to ask my calculator, well, what angle is it? Who cares? All we need are our ratios, and we can find everything that we need. All right, let's try it again. This time, they want you to take the cosine of the inverse sine of negative 1/3. Again, break it down. You take the inverse sine of a ratio, the answer is an angle. You take the cosine of an angle, the answer is a ratio. A ratio is what we need to answer this question. Let's break it down even more. If we take the inverse sine of a negative ratio between 0 and negative 1, and negative 1/3 is, what kind of angle is that function spitting out? A quadrant 1 or a quadrant 4 angle? A quadrant 4. So we know this is a quadrant 4 angle. Draw yourself an angle in quadrant 4 then. Boom. There's my angle, right there. Okay, so if you took the inverse sine of that ratio to get the measure of this angle, that means this angle has a sine ratio of 1/3. So 1 over 3, guys, that's O over H. That's Y over R in his new definition. So let's label a triangle that has that sine ratio. So off of this angle, give yourself an O over H that is 1 over 3. So 1, 3, right? O over H, Y over R. Guys, the ratio was negative. It was negative because if you're an angle in quadrant 4 and you had to go down to that point, what would 1 be? Would it be positive or negative in quadrant 4? It would be negative. Now again, I know we're not supposed to be saying that the sides of a triangle are a negative number. It's really the y coordinate that is representing that side length. So that is a negative 1, and that's why his sine ratio is negative. It's negative 1 over positive 3. All right. If they ask us now we're done. That got us the angle. Now we have to take the cosine of that angle. So the cosine of that angle is the answer to this question. But guys, if I'm going to find the cosine of this angle, that's going to be A over H, X over radius. I need this side in order to find the cosine. So I'm going to have to do a little Pythagorean theorem again to figure out the missing side. So A squared plus B squared equals C squared, right? Or C squared minus B squared equals A squared. So 9, take away 1 is 8, square root it. This is the square root of 8, which is going to be 2 root 2. I'd like to think that we're okay with the Pythagorean theorem part. I'm not writing it down. Again, I'm just trying to save us a little bit of time. Now, guys, think back. If you're in quadrant 1, this side length for your triangle is represented by an x coordinate, right? From the center to there, or the origin to there. Would 2 root 2 be a positive x value or a negative x value for a point in quadrant 4? Positive. So you don't need to add a negative sign. It would be. This would be a positive x coordinate, positive 2 root 2, and it would be a negative y coordinate. That would be the point 2 root 2, negative 1. Okay, so I don't have to add a negative sign because sometimes you got to add it on your own. Now, the cosine of that angle is what? A over H, X over R, it's 2 root 2 over 3. And you're done. Okay?
Question.
Go ahead. Well, 1 second. I think there was a hand. Go ahead, Michael.
Back to A, did you cross out the inverse tangent of 1/2?
Well, because we don't need them anymore. The inverse tangent of 1/2 got us the quadrant 1 angle that we built. So we used him to create an angle inside of a right triangle that had this tangent ratio. So the angle to us, or the inverse tangent of 1/2, once you've built your triangle off of that angle with that tangent ratio, you're just talking about the angle now. So the inverse tangent of 1/2 got you this angle. The sine of this angle is now the answer to the question. Okay? Go ahead, Jay, you had a question?
Yes. How did you get the 2 root over 2?
Because you have to use Pythagorean theorem. A squared plus b squared equals c squared, right? So we knew the 3 and the -1. So we could do c squared minus b squared equals a squared. And then you always square root it to get your a value. So 9 take away 1 is 8. So this side is root 8. Or I should say 8. You take the square root of it is your actual a value. And the square root of 8 simplifies to 2 root 2. Just Pythagorean theorem. I'm just not writing that part down. But it is something that we solved for, okay? All right, let's try it one more time. Now they want the tangent of the inverse cosine of -1/3. All right, well, if I take the inverse cosine of a ratio, the answer is an angle. I take the tangent of an angle, the answer is a ratio. This is a ratio that needs to be my answer. Let's do it a little bit better, though. If I took the inverse cosine of -1/3, right? It's going to spit out, well, inverse cosine spits out quadrant 1 or quadrant 2 angles. Which one is it if the ratio is negative? Quadrant 2. So we know this is going to be a quadrant 2 angle. So draw yourself a quadrant 2 angle. There it is. We have an angle that lands in quadrant 2, but remember, it's really the reference angle that we actually use, which is fine, because the reference angle and the real angle, they both share the same point, the same x and y coordinate, so it's okay. All right, now we're going to build a triangle off of that angle, and let's see what we got. If you took the inverse cosine of this ratio to find the measure of that angle, you took the inverse cosine of that ratio because that is that angle's cosine ratio. So use it. Use that cosine ratio to fill in your triangle. Cosine, again, would be a over h or x over r. So a would be 1, h would be 3. But guys, remember, you're basically labeling this triangle off of an ordered pair that landed in quadrant 2. Would this distance, would this one be positive or negative in quadrant 2? If it literally says this is your x coordinate and you went left, it's a -1. So he gets the negative sign out of that negative ratio, and your radius or your hypotenuse is always a positive value. All right, well, guys, that gets us this triangle right now. In reality, the answer to this question is going to be the tangent of the angle that you just built. If I'm going to find the tangent of this angle, that's going to be O over A, Y over X. I need this side in order to find the tangent. So let's do Pythagorean theorem. A squared plus B squared equals C squared, or C squared minus B squared gets me A squared. So 9 take away 1 is 8. Take the square root of it, that's root 8. Root 8 simplifies to 2 root 2. And now ask yourself, in quadrant 2, would this be a positive or negative y value? Do you have to add a negative sign to this? Guys, in quadrant 2, does this represent a positive or a negative y? A positive y value in quadrant 2. Oh, Lord. All right, so you don't have to add a negative. You're good. All right, we're ready to go, guys. So now you have to take the tangent of this angle to answer this question. And what is the tangent of this angle? O over A, Y over X, it's 2 root 2 over -1. Which is just going to be -2 root 2. And you're done. How do you guys feel? Do you feel okay? Yep. I can do these all day. These feel like little puzzles. I love them. Give me another one. I feel like they're addicting. All right? Okay. Now we can go down. That's still working with our same main inverse trig functions. Inverse sine, inverse cosine, inverse tangent. Now I'm going to show you how the inverse secant and the inverse cosecant work. But again, I almost feel like it's a little bit of a waste of time because in order to do a problem that involves these inverses, they're going to be converted to original trig functions anyway. All right, so I filled them in for you. So guys, here is the graph of the secant function, right? It's the reciprocal of cosine. So it's all these up parabola, down parabola, up parabola, down parabola problems. So what they did is these parabolas won't pass the HLT to create an inverse. So they chopped this parabola in half right at 0, and they chopped this parabola in half right at pi, and they said we're going to keep this portion only. So this half of the parabola got kept, and this half of the parabola got kept. And that's how they make the inverse secant survive. So look at what angles survived. Angles from 0 to pi over 2, and angles from pi over 2 to pi survived his cut. And then ratios from 1 to infinity survived, and ratios from -1 to infinity survived. So now the inverse secant, these ratios are going to go in, but only angles from 0 and pi can come out, because those are the only angles that survived the cut of his graph. So I showed you that. So go to the next page. So when you take those little parabolas and now you plug ratios in, ratios from 1 to infinity, or -1 to -infinity survived, angles from 0 to pi. Now you get these two completely separate curves. So guys, as far as the inverse secant is concerned, if I plug a ratio greater than 1 in, an angle between 0 and pi over 2 comes out. All right, that would be a quadrant 1 angle. So if you take the inverse secant of a positive ratio bigger than 1, it's going to spit out a quadrant 1 angle. Just like the inverse cosine of a positive ratio spit out a quadrant 1 angle. So far he's behaving just like his original trig function. All right, if I plug a ratio less than -1 in, an angle between pi over 2 and pi comes out. Those are quadrant 2 angles between pi over 2 and pi. All right, so you would put your angle in quadrant 2. So now they're saying if you take the inverse secant of a negative ratio between -1 and infinity, it's going to spit out a quadrant 2 angle. All right, so again, the inverse secant of a negative ratio spits out a quadrant 2 angle. So guys, he acts just like his reciprocal. He acts just like the inverse cosine. So we're going to be able to convert all inverse secant problems to inverse cosine problems. They behave the same way. Okay? Let's see the cosecant now. So guys, here's the graph of cosecant, right? Same thing, up parabola, down parabola, they just have a different start point. So now when you want to chop his graph, sorry, I couldn't see it. You chop it from -pi over 2 to pi over 2. So this parabola, half of it, survives his cut, and this half survives his cut. They chop it here and here. So angles between -pi over 2 and pi over 2 survive the cut of his graph. Quadrant 4 and quadrant 1 angles survive the cut of this function's graph. All right, so if we look at his inverse now, now you're going to be able to plug ratios again that 1 to infinity and -1 to -infinity survived. And then angles from -pi over 2 to pi over 2 survived. So if you look at his graph, if I plug a ratio greater than 1 into the inverse cosecant, an angle between pi over 2 and 0 comes out, which is a quadrant 1 angle. just like the inverse sine of a positive ratio spit out a quadrant 1 angle. Then it says, if I plug a ratio less than -1 into the inverse cosecant, if I plug a ratio less than -1 in, an angle between 0 and -π/2 comes out of this graph, a quadrant 4 angle. So yet again, the inverse cosecant of a positive ratio spits out a quadrant 1 angle. The inverse cosecant of a negative ratio spits out a quadrant 4 angle. So he behaves just like his reciprocal's inverse. So he acts just like the inverse sine. So all of our inverse cosecant problems, guys, we're going to convert them to inverse sine problems. They're capable of spitting the same kinds of angles out. Inverse cotangent, I wish he was pretty. He gets his own day because he is not pretty. He does not behave like his reciprocal. Okay. Oh, dear Lord. I'll fill that in. You'll get it. Let's try a problem. So, guys, it says, find the exact value of. They want the inverse cosecant of 2, right? Ratios from 1 to infinity survive on the positive side. So that's a perfectly acceptable ratio. So we know if you take the inverse cosine of a positive ratio, it spits out a quadrant 1 angle, right? He's capable of the same angles as sine, quadrant 1 and quadrant 4. So we're going to turn this into an inverse sine problem, guys. He's capable of spitting the same angles out. So we're going to turn this into the inverse sine of, the inverse sine would have his reciprocal ratio. So if the cosecant has a ratio of 2, what's the reciprocal of 2 that we could apply to the sine then? 1/2. So you just take the reciprocal of whatever ratio they've given you, and you can turn it into the original trig function's inverse. So guys, in this case, the inverse sine of a positive ratio would also spit out a quadrant 1 angle. So now, if they're asking you to find the exact, these must be special ratios, like 30s, 60s, 45s, quadrantals. Guys, does anybody know the sine of what angle had a ratio of 1/2? Was it a 30? A 45, a 60? Anybody know which special angle had a ratio of 1/2? A 30. He's our baby. Sine 30 is 1/2. So it's a π/6. And what version of π/6 landed in quadrant 1 between 0 and π/2? π/6. So the answer to this question is π/6. You just have to reciprocate whatever ratio they have given you. All right. Inverse secant, right? He acts just like the inverse cosine. So they are capable of spitting out quadrant 1 and quadrant 2 angles. If you take the inverse secant of a negative ratio, we learned that it spits out an angle in quadrant 2. Okay? All right, let's turn it into his original trig function. So since they behave the same, we're going to call this the inverse cosine of negative. What's the reciprocal? Guys, this is √2/1. So his reciprocal would be 1/√2. And what does that rationalize to? √2/2. So negative √2/2 is his reciprocal. Okay, does anybody know the cosine of what special angle, 30, 45, 60, had a ratio of √2/2? Anybody know? Was it a 30, a 60, or a 45? A 45. So you have yourself some multiple of π/4 hanging out in quadrant 2. So guys, if this is 4 πs/4, what multiple of π/4 landed in quadrant 2 then? This is 4, this is 1 π/4 less. He has a reference of π/4. This would be 3 π/4. So 3 π/4 is the angle they would spit out that has a ratio of negative √2/2. Okay? All right, last one. If you take the inverse cosecant of a negative ratio, we know he's capable of spitting out quadrant 1 or quadrant 4 angles, just like his reciprocal trig function. If the ratio is negative, it's going to be an angle in quadrant 4. So let's turn this into inverse sine. the inverse sine of, we have to reciprocate this, so it would be negative 3 over 2 root 3. We got to rationalize that. So that would be negative 3 root 3 over root 3 times root 3 is 3, times it by 2 is 6. What's negative 3 over 6 reduced to? 1/2. That's negative root 3 over 2. Guys, if they're going to make you find exact values, your ratio should be root 3s over 2, 1/2, root 2s over 2, zeros, ones, negative ones, right? Like your quadrantals. So the inverse sine of negative root 3 over 2. So guys, the sine of what angle in quadrant 4 had a sine ratio of negative root 3 over 2? Anybody know what's special? Had a sine ratio of root 3 over 2? Well, if sine 30 is 1/2, sine of a what has to be root 3 over 2? Who's the other angle in that pair of triangle? It's got to be a 60. So it's got to be a pi over 3. What version or multiple of pi over 3 landed in quadrant 4 between 0 and negative pi over 2? Not pi over 3, but negative. Michael! Negative pi over 3. Beautiful.
Is that good or?
Beautiful. Beautiful. That's what I wanted you to say. All right? So I hope that's okay, but that's what I meant, like, with kind of flying through their graphs. They just get turned into their original trig functions anyway. So to spend all that time breaking their graphs down, I just felt like I'd rather get to the examples than showing you that graph. All right, so guys, I did make a homework on these reciprocal inverse trig functions. I think I made it due Thursday. So it gives you today, tomorrow, and then Thursday after school to work on these problems. Tomorrow, I'm gonna have to do inverse cotangent. He's a slippery slope, guys. He doesn't act like the inverse tangent. He gets turned into a different trig function. It's wild, all right? But I'll fill this in, guys. It's just the same thing. Inverse secant, inverse cosecant, and so on. I'll have that filled in on your pictured notes. All right? Obviously, if you have any questions, please let me know. Guys, thank you so much for coming. Happy June. We are in June. Let me just double check your attendance really, really quickly. Have a good day, guys. Thank you, guys.